All right, let's look at theorem 1, which says Laplace transform of a convolution of f of t and the g of t is equal to capital F sub s times capital G sub s. All right, so let's try to prove this theorem here. All right, first thing I would do is I'm going to define f of t and a g of t to be 0. If t is less than 0, right? So we can do this because Laplace transform, the integral starts from 0. And so it really doesn't matter what the definition is for f of t and g of t for t less than 0, because it's not going to be considered, right? So we're going to make this assumption here. All right, so let's try to start with the left-hand side, which is the Laplace transform of the convolution between f of t and g of t. All right, so Laplace transform definition goes integral from 0 to infinity, and then you have e to the negative st and f of t, but in this case f of t is f of t convolute g of t. So we have an integral from 0 to t, and f of tau times g of t minus tau d tau, and then dt. So this is dt's for the first integral there. All right, so that's the definition. All right, then one thing we're going to do, first thing we're going to do is here, since we defined that f of t and g of t is 0 for a negative t value, and you can see that as tau goes from 0 to t, and t minus tau is going to stay, non-negative. But if you go beyond t, g of any negative number is going to be defined to be 0. So what we can do is we can actually do this. Instead of stopping at t, we can actually go all the way to infinity, because after t, the integrand is going to be equal to 0. Right? That will make our lives a little bit easier. All right, and the next step is this. Right? Since here, this is an integral with respect to tau, this has nothing to do with tau, so we can put it inside. So we can put this guy inside here, right? And also we can switch, dt and d tau and dt. So we just change the order of integration, and so we can rewrite it as this. Right, so you have a double integral from 0 to infinity, and then you have another 0 to infinity. Right, then you have inside e to the negative st, right, f of tau, and you have a g of t minus tau. And then we switch the order of integration. So you have a dt, d tau. Right, we have that. All right, then next thing we're going to do is we're going to try to pull things out. And here, we're going to split this e to the negative st. Since t is same thing as tau plus t minus tau, right? So we can split it in this way. So you have integral from 0 to infinity, right? Integral from 0 to infinity, right? I'm going to split this. So you have e to the negative s tau. So that's one of them. So e to the negative s tau, right? Then we can multiply by e to the negative s t minus tau. So I'm going to put e to the negative s t minus tau. Right, we got that. Then I'm going to put f of tau here. And then we're going to put g of 1 minus tau. And this is with respect to t. And then we have it with respect to tau. Now, next thing we can do is, since here we have this expression which has nothing to do with t, so we can actually bring it outside because it's considered to be a constant in terms of that integral. So you have integral from 0 to infinity. All right, so you have e to the negative s tau, f of tau. Then we have an integral from 0 to infinity, e to the negative s times quantity t minus tau, g of t minus tau, dt, d tau, right? So, and I'm going to do a little bit of substitution there. I'm going to, so I'm going to go up here. I'm going to let, let's see what letter, we can use probably U substitution. Let U be t minus tau, right? So that we can call this guy right here U, and call this guy U, which makes it look like the Laplace transform of G. All right, so I'll go through the usual drill, take the derivative of U with respect to t, which is going to be obviously 1, which means that we can actually use du and dt interchangeably. All right, so we can write it this way. So this is going to be integral from 0 to infinity, e to the negative s tau times f of tau. Right, this part doesn't change. Oh, I forgot to do the conversion. So originally t is going from, so lower limit is 0 and an upper limit is infinity. Right, if you change that to a new variable u, all right, so let's see, t is starting from 0, so it's going to start from negative tau to infinity minus tau is still infinity, so we're going to do that. So we have an integral from negative tau to infinity, right? Then we have a e to the negative su, g of u, right? dt is now du, right? And then you have a d tau, right? And again, for a negative value, g is going to be 0. So even if you start from negative tau, it's not going to really do anything. So we can actually change that to 0. You can start from 0 because if you plug in negative value for g, then it's for u, then it's going to, g is going to be 0. So we have this integral. And then another thing we can do is, since this inside integral has nothing to do with tau, so we can pull this whole thing, because this is going to be considered to be a constant, you can pull it outside, right? So I'm going to go up here. All right, so we're going to have integral from 0 to infinity, e to the negative s tau, f of tau, d tau. Then you have an integral now from 0 to infinity. You have e to the negative su, g of u, du. Right? All right, so this is going to be, and you can see that, oh, actually, this was equality here. This is equality. All right, so we're doing a chain of equalities. All right, you can see that the first integral is the definition of the Laplace transform of f. So we have a capital F of S multiplied by, if you look at this, this is actually instead of instead of t we're using u, but still it's the equivalent, it's a w variable, so it's the same as capital G of S. All right, so this will verify this theorem 1. All right, that's it. I hope that this was clear.